In this video, we're going to be continuing our analysis of probabilistic functions. This function here is very similar to the previous one. In fact, it is identical in every way except for these last three lines. We have the same if statement and the same for loop setup. All we've done this time is instead of picking a random number between 1 and n minus 1, we're going to 1 to n over 2. And then we're making two recursive calls, both of which have k in there. So, just like we did before, let's begin with the worst case. A problem kind of occurs here, though, because those recursive calls are kind of competing. We have one of size k and one of size n minus k. If we were to plug in values like k equals 1, that would result in one of those recursive calls being small. If we were plugging in a value of k equals n over 2, it results in both of them being divide and conquer. So it's not clear which one would be better. So let's write down what the options are. For our worst case, it's either going to be k equals 1 or k equals n over 2, it seems like. And that is because if we were to plug those in, those are two very distinct scenarios. K equals 1 looks like t of n equals cn plus t of 1 plus t of n minus 1. And k equals n over 2 looks like t of n equals cn plus t of n over 2 plus t of n minus n over 2, which is n over 2. And if you have a good memory, you might remember which one of these is the longer one. It is the chip and conquer style one, the t of n equals c of n plus t of n minus 1. And that is because chip and conquer tends to take longer than divide and conquer. So for our worst case, we are going to be in the situation of k equals 1. But it might not be obvious, and you might need to just consider those different k values and try and find out what happens on your own. We know one thing, which is that t of 1 is just c. So t of n is equal to cn plus c plus t of n minus 1. And we can solve this via substitution, but we might remember that this is very similar to the problem we've seen in the previous example. And I again leave this to you as an exercise to show that this is in theta of n squared. Now let's do the best case. Best case. The best case will be k is equal to n over 2. So if we do that, we have t of n equals cn plus t of n over 2 plus t of n over 2. This is t of n is equal to cn plus 2 copies of t of n over 2. And you might remember that that is actually, in fact, the exact same recurrence relation that we saw when we studied merge sort, and it will also have the same complexity, of course. So I again leave this to you as an exercise to repeat and practice with these things. This should be t of n is in theta of n log n. And again, just like the previous example, our worst case and best cases have different run times, which means that there is a possibility that we get a different expected case. Since this example is very similar to the last one, let's try and approach it in the same way. Let's draw a number line for k and see what happens. We have k, which in this case ranges from 1 to n over 2. And looking at our best and worst cases, we have that the worst case is over here, and the best case is over here by n over 2. And just like we did last time, we want to leverage conditional probability to help us here. So we're going to split the problem up somewhere in the middle. And we're going to be thinking about this in terms of the left side and the right side. So this left side in red is where the worst case is going to be more similar, and this right side might be where the best case is more similar. So let's try and set this up. we're going to try to find the expected time as a function of n. And we're going to say, what is the probability that we are in that left region? K less than, let's call that n over 4 in the middle, times the expected time, given that k is less than n over 4, plus the probability that k is greater than or equal to n over 4, times the expected time as a function of n, given that k is greater than or equal to n over 4. And just to be consistent here, this region over here is going to be the blue part, and the other region is the other term. The probability that k is less than n over 4. There are n over 4 things, or thereabout, out of n over 2 possibilities. This is equal to n over 4 times 2 over n, which is 1/2. If that probability is equal to 1/2, then the other one must necessarily be equal to 1/2 as well. Probability that k is greater than or equal to n over 4 is equal to 1/2. And just like we did before, we're going to start by bounding this. Let's bound it above first and then come back and bound it below afterwards. So we have that the expected time, given that k is less than n over 4, is less than or equal to, we always perform the for loop in the code above, so we always have that cn. And then looking in the red region, we want to make k as large as possible. The worst possible choice for k in that region is k equals 1, the worst case. So that would be et of k, which is et of 1, plus et of n minus k, which is n minus 1. And for our last term, the expected time as a function of n, given that k is greater than or equal to n over 4, that is less than or equal to cn again, plus the worst possible choice of k in that second region is the one closest to the bad side, which is the n over 4. So we'd have an et of n over 4 plus et of n minus n over 4. Let's bring all of that together. So we have et of n is less than or equal to 1/2 times quantity cn. This term is just c. So I'm going to ignore it because it's just a constant. It's not going to affect my runtime. Plus et of n minus 1 plus 1/2 times cn plus et of n over 4 plus et of n minus n over 4 is 3n over 4. So et of n is less than or equal to, if we distribute the 1/2 there, we get 1/2 cn plus 1/2 cn, that's a cn. Plus we now have 3 recursive calls, 1/2 et of n minus 1 plus 1/2 of et of n over 4 plus 1/2 of et of 3n over 4. And just like we've seen in our previous example, we have a chip and conquer intermingling with a divide and conquer, and that doesn't work very well, so we're going to do more bounding trickery. So we get et of n is less than or equal to cn plus 1/2 et of n. I'm again going to replace the chip and conquer with an et of n instead, and then we're going to try to group it together with the et of n on the left-hand side. So plus 1/2 et of n over 4 plus 1/2 et of 3n over 4. Now, as we've seen already, we have a 1/2 et of n here and an et of n over here. We can subtract 1/2 et of n from both sides and group those together. Doing so, I'm left with a 1/2 et of n on the left-hand side is less than or equal to cn plus 1/2 et of n over 4. plus 1/2 et of 3n over 4. Now we have to do some simplification to make this look a little nicer. Let's multiply by 2 to get that coefficient away from the left-hand side. We don't like coefficients being over there. So if I multiply everything by 2, I have et of n less than or equal to 2cn plus et of n over 4 plus et of 3n over 4. And now, just like we've done several times before, we don't like having constants in front of our additional cost there. So let's redefine that term there, the first term, to be c1n plus et of n over 4 plus et of 3n over 4. And now we need to analyze this. This is a lopsided recurrence, and pretty much the only techniques we have for analyzing those are recursion trees. So we're going to have to make a recursion tree here. My additional cost is the c1 of n. So the root of my recursion tree is c1 of n, and it splinters into 2 processes, one of which is size n over 4. So I have a c1 n over 4 here, and a c1 3n over 4, which I can write as 3c1 n over 4. Those then splinter into 2 processes. The left branches in both of those, I'm taking a fourth of what I had above, so this splinters into one of size n over 4. So this is a c1 n over 16. And this is a c1 3n over 16, which is 3c1 n over 16. This one is another 3c1 n over 16. Then the right side is 3 over 4 times 3 over 4, so that's 9 c1 n over 16. Just to make sure that we understand where these things come from, this term was from doing an et of n over 4. This term was from doing an et of 3n over 4. This term was an et of n over 16. An et of 3n over 16. An et of 3n over 16. And an et of 9n over 16. So those are written kind of small, but that's just to remind you where those things came from. We'll continue this process. And then eventually, this left branch will terminate. And then longer down the line, this right branch will terminate. And it's important to remember, we've already given up hope on lower bounding here. We are only upper bounding. So we do not need to necessarily fully analyze this tree. We just need to come up with a reasonable upper bound by using the information in this tree. So what do I mean by that? When we did this before, we used this left branch, the closest node to the root, as a lower bound. So we use this left part as a lower bound. And we use that right branch as an upper bound. So this right branch over here was a upper bound. So this was our upper bound. So I'm not actually going to need to do a whole lot of work with that left branch. Before I can really come up with a good upper bound, I'm going to need to compute the cost at each level of the tree. So the cost at the first level is just c1 of n. The second level, we have a c1 of n over 4 and a 3c1 of n over 4. That gives me 4c1 of n over 4, or c1 of n. The next level, we have 1c1 of n, 3c1 of n, 3c1 of n, and 9c1 of n, all over 16. That will give me a c1 of n again. That will remain true until we get to the first node to terminate, the leaf that is closest to the root. And for everything afterwards, so everything below this line here, we will have that the cost is less than or equal to c1 of n. We're interpolating that pattern for the things below. So we have a good upper bound on the cost at each level of the tree. We now need to determine the height of the tree. To determine the height of that tree, what we're going to have to do is find out how much is the size shrinking at each level. The size is shrinking by 3/4. So we need to solve to find the height. 3/4 to the h times n, that's the size of the recursive call at the level, is equal to the base case of 1. If you remember, we don't like to have a log base less than 1, so I'm going to multiply by 4/3 to the h and get n equals 4/3 to the h, and then take a log base 4/3 of both sides, and we have h is equal to log base 4/3 of n. And now, what do we need to do with this information? We know how many levels of the tree there are, and we know an upper bound on the cost at each level. So, ET of n is less than or equal to the cost at each level, which is C1n, times the number of levels, h, which is log base 4/3 of n. And so, ET of n is in big O of n. And just like we saw in our previous example, it turns out that in this case, we had that our best case was also in n log n, which means that that is definitely a lower bound. So since the best case is in theta n log n, the expected case is in omega of n log of n. I just noticed I had a typo. I apologize. This should be big O of n log n. If it's in big O of n log n and big omega of n log n, the conclusion that we must draw is that ET of n is in theta of n log n.